Hello, thank you for watching this video. My name is Pedro Zufiria and I'm a professor at the Universidad Politécnica de Madrid, UPM, Spain. This work has been developed by Alejandro Jarabo Peñas with the help of Carlos García Mourinho and myself at the Telecommunications School within the Cabify chair. Both the UPM and Cabify are strongly committed to sustainable mobility and to reducing the carbon footprint in cities. And within such framework, we are characterizing the public transport system in the region of Madrid. Precisely, in this work, we analyze the behavior of several lines of urban buses in the city of Madrid. The title of the presentation is Headway Estimation in Urban Buses based on available arrival time estimators. Let me start by remembering the importance of public transport for reducing the contribution of each citizen to the carbon footprint, besides increasing the accessibility and ease of travel in cities. Precisely, in 2018, 420 million trips were made using Madrid's municipal bus system. And the performance of such service strongly depends on the regularity of the headways between the buses. The higher the regularity, the higher the user experience. Let me now show you the contents to be addressed in this presentation. First, we are going to summarize the procedures followed in the research. Then, in section 2, we are going to introduce the two types of available data that had been employed, static and real-time data. After that, in section 3, we will analyze and characterize the data in order to define the criteria to properly clean it. In section 4, we will explain the algorithms that have been used to estimate derived data, such as the position of the buses, the real arrival time of the buses and the stops, and the time between consecutive stops. Then, in section 5, we'll explain the process for obtaining headways using the previously estimated derived data, and we will continue with an analysis of the obtained headway series. Finally, we will state our conclusions and propose possible future lines of work. Let me display now a general summary of the different steps that Alejandro is going to illustrate. First, the data collection of the arrival times at each stop provided by the API. Then, the data analysis and cleansing, where non-consistent instances will be eliminated. Next, the derived data, position, arrival times, times between stops, will be estimated so that finally the headways are estimated and analyzed. Let me now give the floor to Alejandro to continue with the presentation.
Hello, my name is Alejandro and, as pointed out by Pedro, I will continue with the rest of the presentation. The data we have used for our research can be divided into static and real-time data. First, we are going to talk about the static data. The available static data is in GTFS format, which stands for General Transit Feed Data Specification. It contains information of the line, such as the line's shape, the stop's position and name, the schedules, and the fares. From this data, we have built a lines dictionary, which contains the most relevant data of each line, such as the total length, an ordered list of stops with their distances to the beginning of the line, and their destinations. On the other hand, we have real-time data. This data is provided by the Mobility Labs EMTs API, which has a series of methods that return real-time information. The one we have used is the time arrival bus method, which, given a stop identifier, provides information about the next buses that will arrive at the stop. This response is in JSON format, and it contains data such as the line they belong to, the stop identifier, the destination, the bus identifier, the distance remaining for the bus to reach the stop in meters, which we will denote as DSB in the rest of the presentation, and the time remaining for the bus to reach the stop in seconds, which we will denote as TSB in the rest of the presentation. It is also important to mention that we have a limitation in the usage of the API, which is 330,000 daily hits. which force us to select a subset of lines, which are lines 1, 44, 82, 132, and 133, which have 2072 different stops, so we perform a burst of requests to all these stops every 50 seconds, from 7 a.m. to 11 p.m. The subset of lines selected can be seen in this figure. Once we collected the data, we perform a slide analysis and characterization of it, and we establish a set of criteria to clean the data, which we will explain in this section. In order to characterize and analyze the data, we focus on line F with a period between requests of 5 seconds, finding out that the refresh rate, which is the time needed for the API to give a new data instance, had a mode of 5 seconds and a mean of 30 seconds. We also found out that the bus's geolocation was of a very bad quality, because although the locations were very close to the line they follow, as we can see in this graph, they were very distant from their actual location of the buses. Because when the buses were stopped in a stop and we compared the location of the stop with the location of the bus given by the API, we found out that this was very distant, as we can see in this graph, where we connect the position of the bus and the stop, the real position, with the position given by the API, which is this one. Finally, we found out that the bus's speed was constant for approximately 30 seconds, and it had a maximum value of 30 km per hour. While we were analyzing the data, we noticed the appearance of contaminated data instances, which we should avoid using in our algorithms, as they might lead to erroneous conclusions. One example of this contaminated data is the time remaining unusually high, as we can see in figure A, where we have a time remaining very high. And another example of this contaminated instance is that the time distance remaining lower than 0, as we can see in figure B. In order to avoid using this contaminated data, we established a set of consistency criteria, eliminating the rows that did not meet them. The first one is the consistency between line, destination, and stop. The second one is that the distances remaining should be greater or equal than 0 and lower than the line's length. Another one is that the time remaining should be greater or equal to 0, lower than 2 hours, and lower than the time needed to travel through the whole line at 7.2 km per hour. And the final one is that the speed should be greater or equal to 0 and lower than 120 km per hour. Using this criteria, we eliminated 5% of the instances, as they were defective. In this section, we are going to talk about the estimation of derived data, explaining the processes followed to estimate and tracing derived data from the data provided by the API. First, we constructed an estimator of the position of the buses, which is not used in the algorithms, but is used to provide a general idea of where the buses are located. In order to test the performance of this estimator, we obtained the coordinates with a phone along part of the route F, which we use as ground truth data. This path recorded can be seen in this figure. We started here and we ended here. Then the process to obtain this estimation is shown here. Knowing the distance remaining for the bus to reach the stop, we extract the distance from the stop the bus is reaching to the beginning of the line, which we will call as DSB. This is obtained from the static data. Then we calculate how far the bus is from the beginning of the line, which we call as DBB, done as DSB minus the distance remaining for the bus to reach the stop. And finally, we obtain the estimation of the location of the bus as the point of the line whose distance to the beginning is closer to the distance indicated by DBB. The path obtained with our estimation of the position can be seen here, shown in red for the higher period between requests and in blue for the lower period between requests. We also constructed an estimator of the actual arrival time of a bus B to a stop S. To perform this estimation, we follow 3 steps. First, we split the data into different trips of each bus B to each stop S. Then we estimate the bus arrival time using the first data instance, which has a time remaining to reach the stop between 0 and 45 seconds. If no instance satisfies this condition, we use the one with the lowest time remaining to reach the stop. Then we obtain the final estimation of the arrival time as the sum of the actual time when the estimation was made plus the time remaining to reach the stop. An example of how this algorithm works can be seen in this figure, where a bus approaches the stop B, and we obtain the estimation using the first data instance between 0 and 45 seconds, which is this one. This would be the second instance. So our estimation is T2 plus the estimated arrive instance, which is 29 seconds, obtaining our final estimation of the arrival time. Then, using the estimation of the arrival time of the buses to each stop, we developed an estimator of the running time between two consecutive stops, S1 and S2, of a bus traveling through a line. This estimation is very simple, as we only have to subtract the arrival time of the bus to the first stop to the arrival time of the bus to the second stop, obtaining our final estimation of the running time between stops. In this section, which is the most relevant of the paper, we will talk about the headways, defining and remarking its importance in public transport, as well as explaining the process we follow to estimate them, and finally analyzing the headways obtained with this process. A headway is defined as the time interval between consecutive buses, for example B1 and B2. Maintaining these headways as regular as possible has a very positive impact in the public transport, as it minimizes the waiting time of the passengers at the stops. Unfortunately, the configurations where the headways are regular is unstable. If we imagine a situation like the one we have in this figure, where we have bus A, bus B, and bus C, a delay in bus B will cause the headway between A and B to increase, and the headway between B and C to decrease, then increasing the number of passengers waiting for bus B at the stop D, and producing then a higher delay in bus B. On the other hand, an advance in bus B will cause the headway between A and B to decrease, and the headway between B and C to increase, decreasing the number of passengers waiting in the next stop, stop D, and then producing a higher advance in bus B. In the next slides, we will explain the process followed to estimate these headways. But before this, it is important to mention some of the issues we detected while we were analyzing and observing the line's behavior. First, we detected that the buses tried to correct the irregularities in the headways by adding a waiting time before leaving the first stop when switching between the line directions. We also found out that joining buses always appear at the first stop of one of the line directions, and that leaving buses always disappeared after reaching the last stop of the line direction. Because of these reasons, in order to avoid these issues, we improve the quality of the headways obtained, we decided to restrict our analysis to the range between the second and the penultimate stops of each of the line directions. In order to explain the algorithm used to estimate the headways in a clear way, we are going to state the following definitions. First, we have the mean running time between stops A and B, for example, which is estimated making use of the estimator explained in the section before of the running time between stops. So the mean time between non-consecutive stops is, for example, B and E is mean running time between stops B and C plus mean running time between stops C and D plus mean running time between stops D and E. Then we have the time to stop, which is the time remaining for a bus B to reach the stop C, equivalent to the time remaining for a bus to reach the stop we stated before, when the stop is the stop C. Then we have the time to next stop, which is the time remaining for a bus B to reach the next stop. And we have the time to the last stop, which is the time remaining for a bus B to reach the last stop of the line direction. If the last stop is stop E, we have that the time to the last stop of bus B is the time for bus B to reach stop C, plus the mean running time between stops C and E, for example. Then, making use of the definitions explained, the final estimation of the headway is obtained by subtracting the time to the last stop of the bus in front to the time to the last stop of the bus in the back, obtaining our final estimation of the headway between bus 1 and bus 2. An example of how this algorithm works can be seen in this figure, where if we focus on one of the directions, which will be this one, we can see that bus A has a time to the last stop of 52 seconds, which is equal to the time to the next stop of 52 seconds, because the next stop is the last stop, which is stop E. And if we focus on bus B, we can see that it has a time to the last stop of 144 seconds, which is obtained by adding the mean running time between stops D and E plus the mean running time between stops C and D to the time to the next stop. And then subtracting this value to this value, we obtain that the final headway between bus A and B is 92 seconds. Using the algorithm that we have just explained to estimate the headways, we obtain a series of headways that look like the ones shown in this figure, which represent the evolution over time of the time interval between consecutive buses, the headway, in seconds. For example, we can see that the blue headway, which represents the time interval between bus 119 and the bus 118, which increases here and decreases here. We can also see another example, which is the yellow headway, which represents the time interval between bus 118 and bus 8238, which increases here and decreases a little bit here. Observing the headways time series, we can extract some interesting conclusions. The first one is that the duration of the series is very similar and lower than the time it would be needed to complete a trip through the whole line direction. The second one is that consecutive series are negatively correlated. If we have the consecutive headways series between bus 1 and bus 2 and bus 2 and bus 3, we have the bus 2 in common. So the second bus 2 behavior affects both series. And the third one is that overtaking between buses implies the appearance of new headways series. If bus 3 overtakes bus 2, then headway between bus 1 and bus 2 and headway between bus 2 and bus 3 are substituted by the headway between bus 1 and bus 3 and the headway between bus 3 and bus 2, making it complex to analyze the headway's behavior. In order to avoid this disappearance and appearance of the headway series due to the overtaking events between buses, we will introduce the concept of the order of buses entrance to each line direction. This order list has a main differentiation with the method used before, because now bus B1 is the first bus that joined the line direction, no matter if it is really the one closer to the last stop, and bus M is now the last bus that joined the line direction, no matter if it is really the one farther from the last stop. So using this order list of the headways, now the overtaking events are represented by the headways taking negative values instead of disappearing. The headway series obtained after including the ordered list of buses in the algorithm is illustrated in this figure, where as we can see, some headways are taking values under 0, which indicate overtakings. We can see two interesting things in this picture. First, bus 8631 overtakes bus 8635 around 10 past 10. So the headways is lower than 0. This might have been caused by an advance in bus 8631, causing this headway to decrease and this headway to increase. As we can see here, this headway decreases and this headway increases. Then we can also see that bus 4832 seems to overtake bus 8633 around quarter to 11. So the headway takes a negative value. This might be caused by a fluctuation between negative and positive values, as we can see here. which may be due to inaccuracies in the data provided by the API. As we can see, the fact that the overtaking between buses is translated into the headways taking negative values constitutes a big advantage, because it allows for a better and faster interpretation of the different events that are taking place inside the line direction, making this method better than the original one. To end up, I would like to remark the main conclusions of the research performed, as well as proposing future lines of research. The first conclusion is that the data analysis and techniques used in this paper might be of use to other researchers who intend to profit from similar scenarios. In addition, the proposed scheme to obtain the real bus arrival times to the stops has proven to be very useful for the development of headway estimators. It is also important to mention that the estimation of the headways requires precise knowledge of the behavior of the buses of the lines and their analysis, for taking into account specific scenarios. And finally, the two proposed headways estimates are very suitable for monitoring the line behavior, as well as its real-time performance. As a future line of research, we propose performing a statistical analysis on the estimated headways, which can help to develop anomaly detection schemes. As we have now reached the end of the presentation, we would like to thank the help and support received from the university and the Cabify chair, as well as the audience for paying attention to this presentation. If you have any questions, feel free to email us in the emails indicated here. Thank you.